Now let's talk about evidence. What is evidence? Evidence is data or observations of the natural world. So evidence should always be based on data, and it has a high bar to meet in the modern scientific method. That evidence should be reproducible, which means someone else could go out and obtain the same or similar evidence, or evidence that doesn't disagree. The evidence should be quantitative, which means it should be numerically stated, not just in words. And so it's not subjective. Not subjective because it's in words, and also not because it's the opinion of the experimenter. Science shouldn't depend on the personality or the opinion or the politics or the psychological landscape of the investigator. It should be beyond that. It's also never going to be perfect, and that, of course, leads to debate in science over what is enough, over whose evidence or data is better than who else's, in terms of how much they have and how careful they were obtaining it. And so the imperfections of data do become paramount when we talk about science as it's actually done. We can say there is no science without evidence. Assertions must be supported by data. Every claim in science is subject to verification. Back to Feynman's quote, it doesn't matter how smart you are, or how clever you are, or what school you went to. Your claim is subject to verification like anyone else's. Science is data-driven, so progress is made by, in the first instance, gathering more data. That's good. Even better, repeating the experiment. And better still, having someone else repeat the experiment to see they get the same answer. Look at these pictures of Saturn that were drawn, because there was no photography back then, in the first 50 years after the invention of the telescope, from 1610 to 1660. They all come from different sources, from different people, using different telescopes. And the question becomes, which one is Saturn? Which is the one that shows what Saturn really looks like? And we can see with hindsight that it's a silly question. These are all terrible pictures of Saturn. If we want a picture of Saturn now, we just go online and we find a picture taken by the Cassini mission that flew to Saturn through space and took exquisite pictures of its rings in infinite detail and color. But back then, this was the only data you had. And the point is that science always progresses at the limit of observation, and scientists always want more or better data. So with the moving bar of better data and better instruments and better tools, you're often left making decisions with imperfect data. And so in 1650, if you had to ask the question, which is Saturn like of these pictures? Is it the top left image of a planet with two little moons? Or is it like one of the pictures that shows a ring around it? Or dumbbells or barbells around it? Which is the right one? The answer is we don't know. We'd have to find out in detail who had the best equipment, what were the optics of their telescopes, were they making observations under situations of night sky brightness and turbulence that made the images blurred. We'd have to know so much. So we continue to move at the limit of our observation, and we continue to be uncertain because of that. All observations are uncertain at some level, and it's the limitations of the measuring apparatus. So while scientists do speak colloquially about measurement error or observation error, that's actually not a very good word. It's a misnomer because it implies it's a mistake. And of course, sometimes scientists do screw up. They do make mistakes. But in general, observational error just means limitations in the apparatus. And so here, we can see another set of measurements. One measurement of the position of a star, and then the same experimenter with the same telescope goes back maybe on successive nights and measures it a few more times and puts data on a piece of paper, and then does 10 and then 30 measurements. And none of them are exactly the same. And so at any point in this process, you ask the question, where is the star really on the sky? And the point then is, of course, that multiple measurements are needed to define the uncertainty. Taking more data gives a more reliable estimate. In the bottom right, it's the center in X and Y of all the 30 measurements, the mean position. It also gives a measurement of the uncertainty, which is essentially the spread or smearing in X and Y of those data points. Notice that if you only had one measurement, you don't really have a measure of anything. You have a single measurement and no measure of uncertainty, so you don't know how wrong you might be. In astronomy, we have data of different kinds, and we'll just summarize the regimes of data in astronomy. By direct exploration, we've only been to the moon. That's a fraction of 1,000,000 miles. That's the farthest we've been, the only object in the universe that humans have ever stood on other than the Earth. By remote sensing, by sending our clever robotic probes and spacecraft, we've ventured about 1,000,000,000 miles to the outer solar system, to all the major planets, in fact. And we've landed on a couple of those objects. Titan has been visited directly by the Huygens probe, and Mars, obviously, by a number of landers. So by remote sensing and clever instruments, which are essentially extensions of our senses, we've been 1,000,000,000 miles from Earth. Every now and then we get lucky. Pieces of the outer solar system fall to the Earth, meteors. And these samples of the outer solar system tell us about the birth of the solar system, the sun, and the planets. They give us important information about cosmic history going back 4.5 billion years. These free samples come to us from the full extent of the solar system, about 10 billion miles. But that is a tiny, tiny fraction of the observable universe. For most of the universe, for most of astronomy, for most of the science we're going to talk about, essentially for 99.9999, many more nines, % of the universe, including all the stars and all the galaxies, the evidence of astronomy is indirect. It's the electromagnetic spectrum, visible light, starting with Galileo and the first telescope, and then in the last 100 years or so, extensions through technology to much shorter wavelengths than visible light, like X-rays and gamma rays, and much longer wavelengths than visible light, like infrared waves and radio waves. So for this vast fraction of the universe, almost everything we know about astronomy, our evidence is not direct. We don't have samples. We don't have physical contact. We haven't visited these places. And so that is a fundamental limitation of the science of astronomy. And given that, perhaps it's amazing how much we've learned about the universe. And so we come to the end of the second module.